Joining me is Anna Lysyanskaya, Professor of Computer Science at Brown University. Anna, thank you for taking the time to speak with me.
Oh, you're welcome.
We're going to have a conversation talking about quantum computing and how that possesses a problem for encryption that can be much bigger than the Y2K bug. Can you elaborate?
Yes, so most encryption schemes in use today, both encryption and authentication schemes, I should say, are based on the hardness, on the computational hardness of problems that are solvable with quantum computers. So in other words, that means that if a quantum computer can one day be built, then those systems will not provide us the security we need to operate on the internet.
It almost seems as though every single system that we know is very vulnerable. Nuclear codes and banks and even governments are all essentially exposed. How can we essentially solve this issue?
A state-of-the-art quantum computer cannot actually solve these problems just yet. We don't actually have a computer that's powerful enough to crack existing cryptographic systems. We just think that it isn't out of the realm of the possibility that it can one day be built. So we have about 10 years, according to some experts' estimates, to come up with other encryption schemes and authentication schemes that aren't vulnerable to quantum attacks. And we actually have made a lot of progress. So there are encryption schemes and there are authentication schemes that are not, at least not known to be vulnerable to quantum attacks. So the name of the game is to design systems right now such that it would be easy to then patch them up with what we called post-quantum cryptography, namely cryptographic algorithms that are not vulnerable.
What are some of the projects or even research that you're currently working on in the area of cryptography?
So I work on cryptographic protocols, and specifically one important area of my research is anonymous credentials, which are protocols that allow you to convince a service that you're an authorized user of the service without revealing any information about yourself. So you can stay anonymous and still convince, let's say, Huffington Post that you're a contributor. So you should be allowed into the contributor-only area, but they don't actually know which contributor you are. They just know that they are interacting with a legitimate person who should be allowed access. So a lot of my work, in fact, most of my work, is vulnerable to quantum attacks. So if a quantum computer can be built, then large moduli can be factored, or the discrete logarithm problem can be solved, and that would make the anonymous credential schemes that I have worked so long and hard on, would make them insecure. So over the next 10 years, remember I just said we have 10 years to patch up our algorithms and to come up with post-quantum solutions. So over the next 10 years, I have a chance to come up with post-quantum equivalents to the algorithms that I've developed, so that if quantum computers should come into existence, people could still use this technology securely.
What would you say is the hardest aspect of your job?
There are several aspects to my job. One aspect is just solving mathematical problems. And it is fun and challenging and very abstract and sometimes disconnected from reality because we just love mathematical puzzles. And sometimes what's hard is to bring us back to earth, to say, no, it's not just about math. It's about everybody's security. It's about making sure that people can interact online without worrying about being spoofed, without losing their identity, without eavesdroppers understanding what they're doing online. And um, I really enjoy the math. And I also understand and appreciate kind of in broad strokes the importance. But connecting the dots, understanding that no, this math, we really do need to get it right in order for people to live online securely, that can be hard.
You mentioned previously that essentially you only have a 10-year window to come up with a solution. My question to you is, how did other researchers and mathematicians, how did 10 years become that essential deadline?
I don't know if that's a deadline. We don't actually know for sure that quantum computers could be built. I think that we have 10 years to um, think of an alternative, as in 10 years from now, we will have more information about whether or not they can be built. So it's more like we can afford to spend 10 years. 10 years is not a lot of time to come up with alternatives to all kinds of very basic and necessary algorithms. But we already have a lot of good starting points. We already know that, for example, we can base security on certain computational problems that have to do with lattices. So we have a lot of evidence that those particular problems will still stand even once quantum computers are built. If you have a good starting point, if you know which direction you're going, then you start with that. You start by doing things that seem to be doable. That's kind of the next question you ask is, okay, so we have a good candidate for a post-quantum algorithm that already does maybe 90% of what we want, but it doesn't do full 100%. How do we adapt it so that it provides the missing piece? And then you go from there. So right now we have encryption schemes that are secure, even in the post-quantum world, but they're not very efficient. So there are two obvious directions to explore. One direction is, how do we make them more efficient? Perhaps we look at very specific lattices that are more efficient, in which these algorithms become more efficient. Another direction to explore is, well, computers seem to be getting faster every year. Maybe in 10 years, we'll have computers that are much faster, and so it'll be okay. And this is very low-hanging fruit that I just described. Then there are other things that are more interesting, like, okay, we have these lattice-based analogs of signature schemes, and we know some protocols that can use them. Can we then take these digital signature schemes and these protocols and adapt them so that we have anonymous credentials? That's my work, that are based on these post-quantum assumptions.
My next question for you is, you were mentioning about computers, how with even in the next 10 years, computers are updating so quickly. Is that a benefit in your area of expertise, or is that essentially almost your Achilles heel when it comes to trying to stay on top of computing?
No, that's definitely a benefit, because as computers get faster, we can more efficiently run complex algorithms that protect us better. And the idea is that the algorithms, maybe they're not super quick, but as computers get faster, they become faster. But we set them up in such a way that to break the algorithm, an adversary would have to spend more years than the age of the universe. And so we're still kind of in the winning side. So as computers get faster, that's good for us generally.
Anna, do you have any final thoughts that you would like our viewers to know regarding your area of expertise?
So the Y2K bugs, it had drawbacks because a lot of systems had to be updated so that the Y2K wouldn't be an issue. But it also had an advantage, and that is that everybody understood that there's a particular deadline by which they had to modernize. And a lot of people came to appreciate the fact that that things have changed and that we all need uh, to that we are all already using computers and we need to use them better. Perhaps this challenge can also have some benefits, and the benefits are that we will all need to make sure that the systems we use to protect ourselves for everyday security are up to date, that they're modern, and that we appreciate that they need to be in place for everybody's security.
Anna Lysyanskaya, Professor of Computer Science at Brown University, thank you so much for speaking with me.
Oh, you're welcome.